Hi there, my name is Adrian O'Sullivan. I'm doing a PhD in UCC. My PhD is based on control engineering with wave energy, and in the future I'll be dealing with arrays. I'm with MARI and I am getting funded by the SFI. This video is based on my paper Wave-to-Wire Power Maximisation from a Wave Energy Converter, whereas the part 2 of many videos, and this video is about Model Predictive Control. This is the first part where I'll be dealing with the zero order hold and the first order hold part. So what is Model Predictive Control? Unlike classical control methods, you take predictions going into the future and you base the first input at the instantaneous moment based off those future values. So the standard MPC looks like this, where you got a reference point and then you got your output from the system. And what you're trying to do is you've got your reference point right here, and that's the trajectory that you actually want, and then this is the output that you have. What you're trying to do is get the error between these to be 0. And the best thing about MPCs is that with optimal control, which is in a continuous domain, you will need an infinite amount of predictions into the future, whilst with model predictive control you only need a certain amount of values into the future. So that's why it's handy to implement in real life. So as I was saying there, you have your output values at k to n. So n being your last value in your prediction horizon, where the longer your prediction horizon is, the more accurate that your system will be, as it can predict the bad stuff that will be happening in the future. So it optimizes the quadratic equation so that the error between the reference point and the output reaches 0 as soon as possible. The MPC that I will be using in this paper was slightly different. It doesn't take a reference point and the output to minimize the error, but it just does something slightly different. But the main picture is that it fundamentally does the same thing, which minimizes the cost function. So here the cost function, I just drawn it out as a convex kind of graph here. So when you minimize it, it goes right down to the bottom where there is 0 change. So as I was saying there, this isn't based off the conventional MPC, it's based off this, where the cost function is based on the average power absorbed. Where if I plot this in terms of the FPTO force, you'll get this convex function, which is plotted as this graph. And when I'm trying to find the maximum point here, but unfortunately, if you use AMPL or IPOPT, they'll try and find the minimum points here, and then it'll be basically a non-convex equation. So what you have to do here is just polarize it, so just multiply it by -1. So the maximum point is now going to be the minimum point, as I will show here. So just by multiplying by -1, it goes below the axis, where the maximum then becomes the minimum. I'll eventually get it right. Which is the same as the maximum. So I can write this as basically minus p average is equal to 1 over t by the integral of t between 0 and capital T, which is the duration of integration. So what I got here is a zero order hold, and this is the first method I used for the cost, or for making the cost function. So what we got here is the continuous velocity, which is z dot of t, and then we have the PTO force, which is FPTO K. So what we have to do is find the area of this, which is basically a digital way of doing integration. And we have z dot plus z dot plus 1 over 2 and multiplied by FPTO. And we multiply by that by t, which is the sample, where FPTO is constant for one sample. So we can say that since the velocity changes between the samples, we got to do that to get the perfect area. And we can represent the cost function as this value there. You're probably wondering why I used a delta z dot value. And I've seen other methods where you use a backwards and forwards Euler's method. But this brings up errors in the optimization, which has a knock-on effect with the actual power absorption. So this is a closer estimation of the power absorbed. So you can see here that delta z dot is the difference between that instantaneous z dot value minus the previous value. So when you fill that into the equations that you saw on the last slide, you get this value here, where I don't actually use FPTO, I use UD of K, which is just a scale. With the zero order hole modeling, this is a section that's based on the augmentation of the zero order hold. So to put it from just a UD of K value into a delta U of K value, which is just integral action. And then I'm going to be placing the delta Z dot value in and making a new model. So the xk plus 1, that state space system, is just a digitized version of the continuous model. And then replacing the UD of K and VD of K values, we get the augmented version. So the next part is based on the delta Z dot values. And I'm just trying to explain how they're fitted into the new state space matrix. So we got a y by AD minus the identity matrix by the state matrices. And here you got BZ and FZ, but they're not actual BZ and FZ matrices that you saw previously. They're just a bunch of zeros that are put into those new B and F matrices. So now we can see that this is just the top value here, the y by AD minus the identity matrix here, written as AD 2 of 1. So that's row 2, column 1, multiplied by the displacement. And then you got AD 2 of 2, which is the velocity value. And then you got the radiation kernel corresponding minus a single present velocity value. And then you can see here that this is actually the parts where AD and all the column values and row values, that's actually Z dot K plus 1. So then you can say that that's equal to delta Z dot K plus 1. The first order hold method is just a more improved version of the zero order hold. So the difference is that with a zero order hold, for one sample you've got the PTO force, and that's forced to be constant for the entire sample. For the zero order or first order hold method, it's piecewise linear, which means it is it's linearly changing throughout the sample. So this means here that this is the power from the zero order hold method, the z dot k plus z dot k plus 1 over 2 by the PTO force, which is the scale version. And you can see here the first order hold method is z dot k by uf k plus z dot k plus 1 by uf of k plus 1 divided by 2. So it's a trapezoidal rule instead of this kind of backwards Euler kind of trapezoidal hybrid, which is very awkward. So now we can put it into this form here. and it'll go up to z dot k plus 2, 3, 4, 5, all the way up until you can't add the two values together, and you'll get a half value. This half value here, which is z dot k by uf of k, this can be left out because the optimization is going to be based on a uf of k plus 1, which is the value that you want to change it to. In the zero or the whole method, you're calculating u of k, which is the instantaneous movement at that k value, which is right here. But the uf of k value, that's just a change of going from uf of k to uf of k plus 1. So it's not instantaneously changing. So that's not the value you're calculating. So we can write the state space form for the first order whole method right here. And even though it looks a bit awkward with the delta u of f of k plus 1, it's a lot more convenient because the new state matrix A here, as you can see, that doesn't have anything to do with a delta z dot of k. So there's one less state in the system, which is very convenient. So that's that. Hopefully I explained myself well enough. If I didn't, then leave a few comments below. It's always appreciated. This was just an introduction of the modeling and why I wanted to put into these forms to create these cost functions. In the next video, I will be going into how I can conveniently put them into matrix A form. Cool. See you then.